All right, we got another wonderful problem. So this one we're doing more maximum and minimum business. And what we have here is we have the position of two particles. And what we want to know is when is their separation at a minimum. Okay? So we have the position of each of these things, and we want to know when do they get as close as possible. Okay, so let's start writing some things down here. So we're given the position of the first particle as a function of time equals 3t squared plus 7t plus 4. And we're given the position of the second one, x2 equals 5t squared plus 5t plus 1. Did I get all that right? Yes. Okay. So we need to know when is their separation a minimum. All right, so let's think about that. When is the separation a minimum? So first, we might as well come up with some function that I'll call it sep of t, the separation as a function of time, and we'll define it as x2 of t minus x1 of t. So now I'll have a function where I plug in a time and I can see how far apart these two particles were at that time. So it's going to equal, let's see, we're going to have 2t squared minus 2t minus 3. Is that right? Yes. Okay. Now every time we're doing a maximum or minimum problem, we want to do the business where we take the derivative and set it equal to 0. The idea is, imagine there's some curve like this. So here's the maximum point. The slope here is 0, right? Likewise with the minimum, the slope there is 0. So we have this curve, so we're taking the derivative and finding where it equals 0. Okay, so now I take the derivative of separation as a function of time, and I will get 4t minus 2. So now I can solve for when does this all equal 0? When does the slope equal 0? We're solving for that time. So time will equal 2 over 4 equals 1/2. This is the time of their separation. But we don't actually know if it's a minimum or a maximum separation. To do that, we take the second derivative, and that gives us 4, taking the derivative of this right here, and 4 is greater than 0. And the rule is if the second derivative is greater than 0, then you must have a minimum. Okay, and that kind of makes sense. Here's what a minimum looks like. Here the slope is negative, here it's 0, here it's positive. So in this location, the slope is increasing. Therefore, the second derivative of the curve is increasing. So that's what a minimum looks like. And you can do the opposite thing for a maximum. So then we can see what this maximum separation or this minimum separation is. Separation minimum equals the separation evaluated at 1/2. And that's going to equal 2 times 1/2 squared minus 2 times 1/2 minus 3. So that'll equal 1/2 minus 1 minus 3. So that's going to equal 1 minus 2 minus 6 all over 2. So that equals negative 7 over 2. So the minimum separation is with x1 7/2 meters in front of x2. Because look at how I defined my separation. It turns out that the minimum separation is negative, so that means that here's x2, and then 3.5 meters in front is x1. So that's how we make sense of our negative there.